In this lesson, you will learn about L'Hopital's rule. First up, you will learn to use L'Hopital's rule to evaluate indeterminate limits in the form of 0 over 0 or plus and minus infinity over plus and minus infinity. Let's take a look at L'Hopital's rule, which says that if you have the limit as x approaches a of f of x over g of x and it equals 0 over 0, or that same limit equals either plus or minus infinity over either plus or minus infinity. If you have one of those two situations, then the limit as x approaches a of f of x over g of x can be found by doing the limit as x approaches a of f prime of x over g prime of x. It's a pretty amazing rule. In the past, we have used factoring and canceling to handle indeterminate limits. So for example, say we had to do the limit as x approaches 0 of the quantity e to the 2x minus 1 over the quantity e to the x minus 1. Previously, what we would have done is used factoring. Now remember that e to the 2x is just e to the x squared. So it's like we have a squared minus 1 here, which would be a minus 1 times a plus 1. So that means we can rewrite this as the limit as x goes to 0. The numerator will factor to be e to the x minus 1 times e to the x plus 1. The denominator is e to the x minus 1. We can cancel these two factors, so this becomes the limit as x approaches 0 of e to the x plus 1. Now, when we plug in x equals 0, we know that e to the 0 is equal to 1, and then add 1, and this limit is equal to 2. Now that's what we do when we are able to use factoring and canceling. But some indeterminate limits cannot be factored. In certain cases, we can apply L'Hopital's rule, which allows us to take the derivatives of the numerator and denominator separately from each other, then find the limit of the new function that results. And that's what this rule is saying. If we have the case where the limit as x approaches a of f of x over g of x is either 0 over 0 or some form of infinity over some other form of infinity, then what we can do is take the derivative of the numerator and put it over the derivative of the denominator and take that limit. So now what we're going to do is take a look at this same exact limit, but this time we're going to do it using L'Hopital's rule so that you can see how it works out to be the same thing. Now if we were to try plugging in x equals 0 here, we would have e to the 0 minus 1. Well, that's 0. And in the denominator, we would have e to the 0 minus 1. Again, that's 0. So we have the case of 0 over 0, which is this first part of the hypothesis of L'Hopital's rule. That tells us that we can apply L'Hopital's rule, and I'm going to abbreviate that with an L apostrophe H. So if we apply L'Hopital's rule, then this becomes the limit as x approaches 0 Now, L'Hopital's rule says take the derivative of the numerator separately from the derivative of the denominator. So the derivative of this numerator would be e to the 2x, and then chain rule says you got to take that times 2. The derivative of the denominator would just be e to the x. Now we can simplify this because we have two exponentials with like bases. So this becomes limit as x approaches 0, e to the 2x over e to the x is just e to the x. So this is 2e to the x. Now we can go ahead, plug in x equals 0 into the limit, and we get 2 times 1, which is just 2. So you can see that we get the same result as we did before, and that L'Hopital's rule does work. So when you have a limit that's in the form of 0 over 0, or plus or minus infinity over plus or minus infinity, then you can apply L'Hopital's rule, which says take the derivative of the numerator separately from taking the derivative of the denominator, and then perform the limit on that new rational expression. In this example, we have to evaluate each limit. Here, we have the limit as x approaches 3 from the right of the square root of the quantity x squared minus 9 over the quantity x minus 3. The first thing we always try is plugging in the limit value. If we put 3 coming from the right into the numerator, then we would get 9 coming from the right minus 9, which is going to be 0 from the right. So that's good because that means we're allowed to take the square root of that number. In the denominator, if we plug 3 coming from the right in, we would get 0 coming from the right. So because we have 0 over 0, that tells us that we are allowed to use L'Hopital's rule. And now here, we would get the limit as x approaches 3 from the right, taking the derivative of the numerator, we would have 1/2 quantity x squared minus 9 to the negative 1/2. Chain rule says times the derivative of what's inside, which is 2x. Taking the derivative of the denominator, we get 1. So this becomes the limit as x approaches 3 from the right of x over the square root of x squared minus 9. Now that we've simplified, we try plugging in the limit value again, and we would get 3 over 0 plus, which of course is positive infinity. Next, we have the limit as x approaches infinity of the quantity 3x squared plus 2x minus 9 over the quantity 6x squared plus 7. We always try plugging in the limit. If we put x going to infinity in the numerator, that would equal infinity. And if we put x going to infinity in the denominator, that would also equal infinity. Because we have infinity over infinity, we are allowed to apply L'Hopital's rule. Now this is going to become the limit as x approaches infinity of the derivative of the numerator, which would be 6x plus 2, over the derivative of the denominator, which would be 12x. Now, if we tried plugging the limit value in, once again, this would be infinity in the numerator over infinity in the denominator, which means, once again, I'm allowed to apply L'Hopital's rule. So this becomes the limit as x goes to infinity of the derivative of the numerator, which is 6, over the derivative of the denominator, which is 12, and this is equal to 1/2. Now, using L'Hopital's is not the only way that we could have found this derivative, but I'm just trying to show you that it's a way that will work. Here we have the limit as x approaches 1 of natural log of x over the quantity x squared minus 3x plus 2. We always try plugging in first, and this would equal the natural log of 1 is 0 in the numerator, and in the denominator we would have 1 squared, which is 1, minus 3, which would be negative 2, plus 2, which is 0. So because we have the situation of 0 over 0, we are allowed to apply L'Hopital's rule, which means that this is going to equal the limit as x approaches 1 of the derivative of the numerator. So the derivative of natural log of x is 1 over x over the derivative of the denominator, which would be 2x minus 3. Simplifying this, we have the limit as x approaches 1 of 1 over x times 2x minus 3. Now let's try plugging in the limit value. It would equal 1 over 1 times negative 1. So this limit is just equal to negative 1. Here we have to evaluate the limit as x goes to infinity of x to the 5th over e to the x cubed. We always try plugging in the limit value first using direct substitution. So we would get infinity in the numerator, and we would also get infinity in the denominator, because e to the infinity cubed is certainly infinity. That tells us we can apply L'Hopital's rule. So this will become the limit as x approaches infinity of the derivative of the numerator, which is 5x to the 4th, over the derivative of the denominator, which would be e to the x cubed, and then applying the chain rule, times 3x squared. We need to simplify, so we get the limit as x goes to infinity. In the numerator, we will end up with 5x squared, because the x squared in the denominator cancels out 2 of the x's in the x to the 4th. And then in the denominator, we will have 3 e to the x cubed. Now if we try plugging in with direct substitution again, 5 times infinity squared would be infinity, and 3 times e to the infinity cubed is also infinity. So that tells us that once again we can apply L'Hopital's rule, and then this is going to equal the limit as x goes to infinity of the derivative of the numerator, which would be 10x, over the derivative of the denominator, which would be 3e to the x cubed, chain rule, times 3x squared. So now we need to simplify this expression, and it's equal to the limit as x goes to infinity. The x in the numerator will cancel one of the x squareds in the denominator, so we will just have 10 left in the numerator. In the denominator, we will have 9x times e to the x cubed. Now that we've simplified, the next thing we always try is plugging in this limit value. Now in the numerator, we just have a constant of 10, and in the denominator, we would have 9 times infinity times e to the infinity, which of course is going to be infinity. 10 over infinity is equal to 0. In part 2, you will learn how to use L'Hopital's rule to evaluate indeterminate limits in the form of 0 times infinity or infinity minus infinity. In this example, we have to evaluate each limit. Here we have the limit as x approaches 1 from the left of 1 minus x times the tangent of pi x over 2. If we just try plugging in 1 minus 1 from the left would give us 0 plus, and plugging in a 1 for x here, we would have the tangent of pi over 2, and we know as we're coming in from the left of pi over 2 on the graph of tangent, it's going off to positive infinity. There's a vertical asymptote there. When you get a limit in this form, you cannot apply L'Hopital's rule yet. So we have to reformat it to try to get it into the forms we can use L'Hopital's with, which are 0 over 0 or infinity over infinity. Now, if we rewrite this as the limit as x approaches 1 from the left of 1 minus x, and what I'm going to do is take that tangent and move it to the denominator so that it becomes cotangent. The argument would still be pi x over 2. Now, when we plug in our limit value, we get 0 in the top. It's actually 0 plus. And in the denominator, when we plug in 1 from the left, that means this argument will be pi over 2 from the left. Now, if we look at the graph of cotangent, when you're coming into pi over 2 from the left, you can see that the y value is going to 0 through positive numbers. So that's going to be 0 plus. Now, because we have 0 over 0, now we can apply L'Hopital's rule. and this is going to become the limit as x approaches 1 from the left. We have to take the derivative of the numerator, which would be -1, and we have to take the derivative of the denominator. Now, the derivative of cotangent of some stuff we know is negative cosecant squared of the stuff, so pi x over 2. Then chain rule says we have to take that times the derivative of what's inside, and we have pi over 2 as a constant multiplying the x, so the derivative is pi over 2. We can simplify this to be the limit as x approaches 1 from the left. The negative in the top and the bottom will cancel, so we have 1 in the numerator. I'm going to bring this constant of pi over 2 out front in the denominator. And then we have to do the cosecant of pi x over 2 and then square that value. Now, most of us think better in terms of sines and cosines, so it would be okay if we rewrote this as the limit as x approaches 1 from the left of 2 over pi times the sine of pi x over 2 squared. We just take the reciprocal of what we had. Now if we plug in the limit value, we would get 2 over pi. Now when we plug a 1 in for x, we're taking the sine of pi over 2, which we know is 1. We have to square it. So this is just equal to 2 over pi. In this example, we have to evaluate the limit as x goes to infinity of the cosecant of 1 over x times the quantity e to the 1 over x minus 1. As always, we try direct substitution first. So if we were to plug in x going to infinity, we know 1 over x will go to 0, and we would have the cosecant of 0, and then we would have to multiply that times e to the 0 minus 1. We know that cosecant has a vertical asymptote at 0, so it will matter whether we're coming from the right or coming from the left to decide whether the graph is going to plus infinity or minus infinity. As x goes to positive infinity, 1 over x is going to go to 0 through positive numbers. Then that means on the graph of cosecant, we are approaching 0 from the right, which means at that vertical asymptote, it's heading off to infinity. Now e to the 0 is 1. 1 minus 1 is 0. So we have this situation now where we have infinity times 0. That means we are not allowed to use L'Hopital's rule yet. So we have to do a little bit of work to get it in format so that we can use L'Hopital's rule. So let's rewrite this into the limit as x goes to infinity. Let's leave this e to the 1 over x minus 1 in the numerator. And let's move the cosecant to the denominator, turning it into sine. The argument will still be 1 over x. Now, let's evaluate. If we put infinity in for x, this becomes e to the 0, which is 1, minus 1, we would get 0 in the numerator. In the denominator, 1 over x is 1 over infinity, which goes to 0. Sine of 0 is 0. And because now we are in the form 0 over 0, we are allowed to use L'Hopital's rule. Now this will become the limit as x goes to infinity. We have to take the derivative of the numerator, which would be e to the 1 over x. Chain rule says take it times the derivative of 1 over x, which is negative 1 over x squared. Because 1 over x is x to the negative 1, so its derivative becomes negative x to the negative 2. In the denominator, the derivative of sine of some stuff is going to be cosine of the stuff. Chain rule says take it times the derivative of the stuff, which would be negative 1 over x squared. Now that's pretty convenient because these are going to cancel now. So we can write this in a simpler form as limit as x goes to infinity. The numerator is e to the 1 over x over the denominator, which is cosine of 1 over x. Now let's try plugging in the values. If we put infinity in for x, the numerator becomes e to the 0. The denominator becomes cosine of 0. We know that e to the 0 is 1. Cosine of 0 is 1. So this whole thing becomes 1. Now we have the limit as theta goes to 0 plus of the quantity cotangent theta minus cosecant theta. We always try direct substitution first, so let's plug in, and we have to do the cotangent of 0 plus minus the cosecant of 0 plus. Now we know there's a vertical asymptote at x equals 0 on the graph of cotangent, and when we're coming into 0 from the right, we can see that the graph is going off to positive infinity. Next we look at the graph of cosecant, and we see there's a vertical asymptote at x equals 0 there, and as we come into x equals 0 from the right, that's also going off to positive infinity. So what's happening here is we have infinity minus infinity, and that's an indeterminate form, and we are not allowed to use L'Hopital's on that, which means we need to do a little bit of work to simplify this limit. So this is going to equal the limit as theta goes to 0 from the right. Cotangent theta can be written as cosine theta over sine theta, and we have to subtract cosecant theta, which can be written as 1 over sine of theta. Then this will equal the limit as theta goes to 0 from the right of cosine theta minus 1 over sine theta. Now, if we try plugging in right now, the cosine of 0 is 1. 1 minus 1, we would get 0 in the top. The sine of 0 is also 0. Now, because we have 0 over 0, we are allowed to use L'Hopital's rule. So then this will become the limit as theta goes to 0 from the right. We have to take the derivative of the numerator, and the derivative of cosine is negative sine of theta. In the denominator, we have to do the derivative of sine theta, which is cosine theta. Now we can try plugging in again. We have the negative sign, and sine of 0 is 0, cosine of 0 is 1, and negative 0 over 1 simplifies to 0. In part 3, you will learn how to use L'Hopital's rule to evaluate indeterminate limits in the form of 0 to the 0, 1 to the infinity, or infinity to the 0. In this example, we have to evaluate the limit as x goes to 0 from the right of x to the x. Now, trying direct substitution, when we plug in our limit value, we would get 0 plus raised up to the power of 0 plus. So that means we have the form 0 to the 0. Now, the problem here is that when the base is 0, it's trying to make the entire expression 0. But when the exponent is 0, it's trying to make the entire expression 1. So there's a war going on between the forces trying to drive the expression to 0 and the forces trying to drive the expression to 1. So we have to do a little bit of work here to see what's going to happen. Now, the technique for this is to let L equal the limit as x goes to 0 from the right of x to the x. And then we're going to take the natural log of both sides. So we have the natural log of L is going to equal the natural log of the limit as x goes to 0 from the right of x to the x. Now, because natural log is a continuous function, it doesn't matter whether we take the natural log of the limit or the limit of the natural log. We can do it in either order. So we choose to reverse the order and do the limit first and move the natural log inside. So, leaving the left-hand side alone, we have natural log of L is equal to the limit as x goes to 0 from the right of the natural log of x to the x. So instead of doing the limit first and then taking the natural log of that value, we can do the natural log first and then take the limit. Now, the reason we want to be able to do that is because the natural log allows us to take that exponent and bring it down front. So now we have the natural log of L is equal to the limit as x goes to 0 from the right of x natural log of x. Now let's check the form we have. If we plug in, we would get 0 times the log of 0. Think of the graph of natural log. As x approaches 0 from the right, the graph is going to negative infinity because there's that vertical asymptote there. Now this is not a form where we can apply L'Hopital's rule yet. So that tells us to try to manipulate this expression in here to see if we can get it into a L'Hopital's form. Now the left-hand side is still natural log of L. The right-hand side is the limit as x approaches 0 from the right. And what we're going to do is leave this natural log of x in the numerator. And we're going to take x and write it as an equivalent expression in the denominator, which would be 1 over x. We know that if we have 1 over x in the denominator, it becomes x in the numerator. So now, if we check by doing direct substitution, plug 0 from the right into the numerator, natural log of 0 coming in from the right we know is negative infinity. In the denominator, if x goes to 0 from the right, then 1 over 0 plus goes to positive infinity. Now that we have a form of negative infinity over positive infinity, we are allowed to use L'Hopital's to get to the next step. We bring down the left-hand side, which is natural log of L. On the right-hand side, we have the limit as x goes to 0 from the right. Now in the numerator, we need to take the derivative, and the derivative of natural log of x is 1 over x. In the denominator, we have 1 over x, which is x to the negative 1. That derivative would be negative x to the negative 2, so negative 1 over x squared. In the next step, the left-hand side is still natural log of L. The right-hand side, we have the limit as x goes to 0 from the right of negative x, because we have 1 over x, which would be multiplied by a negative x squared, so the result is negative x. Now we can go ahead and apply the limit on that right-hand side. If we plug a 0 in for x, the right-hand side becomes 0. Now this is the natural log of L, so if we want to get to the variable L, we need to take e and raise it up to the power of the left-hand side, and take e and raise it up to the power of the right-hand side. So we get e to the natural log L equals e to the 0. Simplifying, we get that L is equal to 1. And now remember who we defined L to be way back at the beginning of the problem. L was defined to be the limit as x goes to 0 from the right of x to the x. So that means that limit is equal to 1. In this example, we have to evaluate the limit as x goes to 0 from the right of the quantity 1 plus x raised up to the cosecant x. Now, to determine if the form we have is something we can evaluate using L'Hopital's, we need to do a direct substitution. So when we plug in our limit value, of course this base is going to be 1 plus 0, which is 1. Now the exponent would be cosecant of 0 from the right. So on the graph of cosecant, coming into 0 from the right, the graph is going to positive infinity at that vertical asymptote. And now this sets up another race condition, we call it. The base is trying to force the expression to equal 1, whereas the exponent is trying to force the expression to become huge. So there's the war going on, or we call it the race. The base is racing towards 1, the exponent is racing towards infinity. So we have to do some work here to try to simplify it. So we will use that same technique where we let L equal the limit as x goes to 0 from the right of 1 plus x raised up to the power of cosecant x. Then we will take the natural log of both sides. So we have natural log of L is equal to the natural log of the limit as x goes to 0 from the right of quantity 1 plus x raised up to the cosecant x. The left-hand side we bring down natural log of L equals. Now because natural log is continuous, we can take the natural log of the limit or we can take the limit of the natural log. So we choose to switch these two and do them in the reverse order. So we have limit as x goes to 0 from the right of the natural log of 1 plus x to the power of cosecant x. We continue to bring down the left-hand side, natural log of L. On the right-hand side, we have limit as x goes to 0 from the right. Because we have a natural log here, we can take this exponent and bring it out front. So now we have cosecant of x times natural log of 1 plus x. Now let's check the form that we have. If we plug in 0 into the cosecant function, we know as x approaches 0 from the right, cosecant is going off to positive infinity. Here, if we plug 0 into the log function, we know that the natural log of 1 is equal to 0. Now we can't apply L'Hopital's in this form because we need to get to 0 over 0 or infinity over infinity. So let's do a little work here. We have natural log of L on the left equals the limit as x goes to 0 from the right. We are going to create a rational expression. In the numerator, we will leave that natural log of 1 plus x, and we will move cosecant into the denominator, which means it becomes sine. We know that cosecant of x is the same as 1 over the sine of x. Now let's check the form that we have. If we plug 0 in for x, the natural log of 1 is equal to 0, and the sine of 0 is also 0. So that tells us we are allowed to use L'Hopital's to get to the next step. The left-hand side remains the same, natural log of L. On the right-hand side, we have limit as x goes to 0 from the right. In the numerator, we have to find the derivative of natural log of 1 plus x. So that would be 1 over 1 plus x. In the denominator, we need to find the derivative of sine of x, which is cosine of x. So we have the natural log of L on the left-hand side. And on the right-hand side, let's go ahead and do this limit. In the numerator, we would have 1 over 1. In the denominator, we will have cosine of 0, which is also 1. So now we know that the natural log of L is equal to 1. To get at the L, we need to take an exponential whose base is e to both sides. So e to the natural log of L is equal to e to the 1. So we know that L is equal to e, and way back at the beginning of the problem, we had defined L to be the limit as x goes to 0 from the right of 1 plus x to the cosecant of x. And we now know that that is equal to e. In this example, we have to evaluate the limit as theta goes to pi from the right of cotangent theta raised up to the power of sine of theta. Now we use direct substitution to decide if we have a form that we're going to be able to work with in L'Hopital's. As theta approaches pi from the right, the graph of cotangent of theta is approaching positive infinity because there's a vertical asymptote there. And as we come in from the right of pi, the y value heads to positive infinity. We know that the sine of pi is 0. So once again, we have this race condition where the base of the expression is trying to do something different than the exponent is. In this case, the base is trying to make the expression get as big as possible and go off to infinity. The exponent is trying to drive the expression to equal 1. So now we will use that technique we are getting familiar with, where we let L equal the limit as theta goes to pi from the right of cotangent theta raised up to the power of sine theta. Next, we take the natural log of both sides. We have the natural log of L is equal to the natural log of the limit as theta approaches pi from the right of cotangent theta raised up to the sine theta. The left-hand side remains natural log of L. On the right-hand side, because the natural log is continuous, we know that the log of the limit is the same as the limit of the log. We can switch the order that we do these two and make it the limit as theta goes to pi from the right of the natural log of cotangent of theta raised up to the power of sine theta. The left-hand side stays the same, natural log of L. We still have the limit as theta goes to pi from the right. Because we have the natural log here, we can take the exponent and bring it out front. So it becomes sine of theta times natural log of cotangent theta. Now let's check the form here. We know that the sine of pi is 0, and the natural log of the cotangent of pi, well, cotangent of pi from the right is going to be infinity, and the log of infinity is also infinity. So we don't quite have it in a form where we can do L'Hopital's yet. Left-hand side is natural log of L. Right-hand side is limit as theta approaches pi from the right. We want to turn this into a rational expression. We will keep the natural log of cotangent theta in the numerator, and we will send sine to the denominator by turning it into cosecant theta. 1 over cosecant theta is the same as sine theta. Now let's check the form. Remember that the cotangent of pi from the right is infinity. The natural log of infinity is also infinity. Cosecant of pi coming in from the right, when we look at the graph of cosecant and it's approaching pi coming in from the right, we see that that's going off to negative infinity. Now when we have this form, infinity over a negative infinity, we are allowed to use L'Hopital's to get to the next step. So now we will have the natural log of L is equal to the limit as theta approaches pi from the right. We have to take the derivative of the numerator, so the derivative of natural log of cotangent theta. We will be using the rule of u prime over u. So the derivative of cotangent of theta is negative cosecant squared of theta. That's the u prime. We have to put that over u, which is cotangent of theta. The derivative of the denominator, since it's cosecant theta, is going to be negative cosecant theta cotangent theta. Then we have that the natural log of L is going to be the limit as theta approaches pi from the right. Now we have this negative sign will cancel with this negative sign, so those are gone. We have a cosecant squared theta being divided by a cosecant theta, so we will have a cosecant theta left in the numerator, and then this cotangent theta in the denominator will multiply this cotangent theta in the denominator, and we have cotangent squared theta left in the denominator. You can also look at it as changing it into a multiplication problem where you have cosecant squared theta over cotangent theta times 1 over cosecant theta cotangent theta, and maybe it's easier for you to see the combination there. The cosecant will cancel with 1 in the numerator, and the two cotangents will multiply to become cotangent squared in the denominator. Let's continue to simplify. The left-hand side is still natural log of L. On the right-hand side, we have the limit as theta goes to pi from the right. Let's go off on the side and simplify this trig expression here. We know that cosecant of theta is 1 over the sine of theta. That's in the numerator. In the denominator, we have cotangent squared theta, which is cosine squared theta over sine squared theta. So we have this numerator being divided by the denominator. So we can turn that into 1 over the sine of theta times the reciprocal of the denominator, which is sine squared of theta over cosine squared of theta. Now the sine theta here will cancel 1 of the sine squareds up in the numerator, so we end up with sine of theta over cosine squared theta. And let's take this expression and bring it into our limit. Sine theta over cosine squared theta. Now we have natural log of L is equal to, let's go ahead and do this limit now. We can take pi, plug it in for theta, sine of pi is equal to 0. The cosine of pi is -1, and we have to square that. So now we have the natural log of L is equal to 0. We need to do the exponential to undo the natural log. So we have e to the natural log of L is equal to e to the 0, which means L is equal to 1. And now we have to substitute back for this L, which at the very beginning we said let L be the limit as theta approaches pi from the right of cotangent theta raised up to the power of sine theta. And now we just discovered that that limit is equal to 1.